Good afternoon everyone, and welcome to this video. Today we are going to be solving the natural logarithm of I to the power I. So first thing what we do is using the normal logarithm rules. We bring the I down, and this will become I natural logarithm of I, using just normal logarithm rules. Now what we can do is we just make a dotted line here, we can represent I using Euler's formula as e to the pi over 2 I. And if we draw that on a complex plane, it can easily be seen. So we have the real axis, the imaginary axis, and since I is just 1, it's 1 times I, so we can represent that point here as 1. And using the complex plane where we measure the angle from the horizontal axis, from the positive, so from here, if you just find the angle, that is pi over 2 radians. However, it should also be noted that we can rotate this as many times as we like. And what I mean by that is essentially this angle pi over 2 can be extended again and can reach the same point. It can be done even again. It can go again, it will reach the same point. And even counterclockwise, even clockwise, I'll use a black colour. I like black. We can go even the other way round. So how do we represent this? Well, it's actually quite simple. It should be noted that every time we go round, and this works for any point in the complex plane, any time we go round, it's 2 pi radians. As you know, 2 pi radians is the full circle. So we can represent I as e to the pi over 2 I plus 2 pi, the circle, k I, where k is in the set of integers. Now integers are both positive and negative whole numbers, so that accounts for the clockwise and anti-clockwise direction of the 2 pi movement. And this I've got this equation here by using Euler's formula, which is e to the I theta equals cos theta plus I sine theta. Okay, so let's continue by substituting the I that we have over here into here. Now we're not going to be substituting it into the I which we've just brought down, since it will not help us out in the future, and you'll see why later. It is very tempting, however, I think after trial and error you'll notice that it just becomes a messy blob. So let's continue. So we have I, the natural logarithm of I, is equivalent to I, the natural logarithm of e to the pi over 2 I plus 2 pi ki, like so. And then again, if we use the normal logarithm rules, we can bring this blob here, and we can bring it down. So this would then be equivalent to I multiplied by pi over 2 I plus 2 pi ki, and then multiplied by the natural logarithm of e. Just make a little barrier there. So I hope we all understand how that happened. This is all in brackets, and then like we did previously, over here where we brought the I down, similarly we bring the this blob down. So let's continue. So as we know, I times I multiplied by I equals minus 1. So here all we have to do is expand the brackets, and it could also be noted that the natural logarithm of e over here is equivalent to 1. So we can just remove that. Okay, let's continue now. So this is equivalent to pi over 2 I times I plus 2 pi k I times I, which is minus pi over 2 plus, well, we will do minus 2 pi k. Now, what should also be noted is that the plus and minus here doesn't really matter. This is also equivalent to minus pi over 2 plus 2 pi k, as long as both are in the set of integers. And this is because integers contain both the positive and negative natural numbers. So the plus and minus can always be changed. For example, here if I substituted k equals 3, here I just need to substitute k equals minus 3 and it'll be exactly the same. So we can write it in both ways, it doesn't really matter. But the key thing here is to notice that we do have this 2 pi k, and it's something which most people will forget. However, it's extremely important because, as we see from the complex plane, there are infinitely many ways to represent I. And to express that in a really nice, coherent way, we do this. So that is the final answer. Hooray! Let's make that a nice colour now. Yay! Thank you for watching my video.